So this is a definition of real. A real number is a Dedekind cut. Okay. So a real number is a Dedekind cut. A real number can be seen as a subset of rational numbers. Can be seen as a subset. So real numbers can be seen as subsets of rational numbers. So just like in, if you remember, rationals were built from integers, right? M and N, right? Reals can be seen, and all of this is kind of like informal. Reals can be seen as can be we can think of them as being built from rationals. Okay, so for instance, you have a rational number line, and in this rational number line, we have a gap. So there's a hole right there. That hole, if we can stick our cut into that hole. So the cut is what? Cut is a subset of rational numbers is what a cut is. So what the cut is this thing here. So let's say this is pi. We just stuck in an irrational number in a rational number line. This is what was missing here. This is a real number, and all real numbers, including 1. So for instance, because all rational numbers are real numbers, but let's say 1 is a real number too. So let's have.
So if 1's a real number, then it's also a cut.
It's also a cut. And let's say we put 1 here. This is 1. So pi can be represented by all the rational numbers to its left. Including negative numbers as well. As a real number, if you think of, because a real number's definition is that it's a subset of rational numbers. If you think of 1 as a real number, then all the rational numbers to the left of 1 represent. 1 is then represented by, if you think of 1 as a real number, then 1 is represented by all the rational numbers to its left on the rational number line.
The real one is
Mhm.
represented by all the numbers just left on the
Yeah.
rational number. So if you say,
Hmm.
I've got one,
Hmm.
and you're talking about a real one, then you could say, I've got two rational, or negative two rational. Or is
Hmm.
it represented by the sum?
Not the sum. The
Any one of those numbers is represented.
everything from here all the way to infinity, you stick it in a set. So that would be, let's say 0.999 all the way to infinity. This thing is 1. So in other words, it's kind of like a weird situation. It's very informal. So, and it's easy. That's why they have them in the books. So for instance, let's say we had pi here, right? So pi is definitely a real number, right? And this is minus infinity. Pi is represented by this subset of the rational number line, minus pi, 1, comma 999. We have pi is what, 3, right? So we've got 2 here. We even have 3 and maybe a little bit more. Pi is 3.141. So we could have this guy here maybe. Now pi is represented by everything to the left from this point on the rational number line.
This makes perfect sense, but one's now a whole because we made it real.
We're thinking of it as that there was a hole and we put it there, and then we're pretending that. But all real numbers have all real numbers, including 1, it's a real number. Yeah. It can be represented by a subset of rational numbers to their left on the. Okay, so now a couple of interesting things happen. Number one, this thing, 1 is a set, right? 1 is a set, and so 1 can be seen as a set that is subset of the other subset pi. I just wrote it here.
Oh, yeah. So 1 is a subset of pi.
Yeah. Yeah. So now it's getting kind of interesting. If we think of 1 as a subset of all the rationals to its left, and pi as a subset with all the rationals to the left, including all the real numbers, right, on the way. So now, if we think of this as a subset, then this not subset, yeah, subset. This subset is a subset of this, which is the bigger one, right? And if we think of them as numbers, as reals, then we can use the less than.
Oh, we can't use the less than on the rational number line. Well, we could.
No, they are. So this guy's to the left. So it is. We can use the rational number line to see that 1 is to the left of pi, therefore is smaller than pi. So when we think of them as reals, and of course we could just replace q with an r, and that would work as well. But here, not work as well, but then it would be more clear. If we see 1 as a set and pi as a set, then 1 is a smaller set, and everything in 1 from here to here is included in the second line here.
So the set of pi just has more.
Yes, pi is a subset. Pi is represented by more rational numbers than 1 is.
Yep.
Even though they go to infinity, minus infinity. Okay. Belding and Mitchell again. And we're going to look at the definition of Dedekind cuts. All right. And the statement of the definition goes, a Dedekind, of course, was a mathematician. A Dedekind cut is a subset, and we're going to call it alpha, is a subset alpha of, is a, I should do this in red, is a subset alpha of the rational numbers. Rational numbers Q with the following properties. One says alpha is not empty and is not equal to Q. And actually they did it like this. So I'm going to take this off, and they did an alpha not equals Q. This should remind you of something, right? Least upper bound. Behind this is LUB is going on, kind of, right? If a set is not empty and has an upper bound, then it will have a least bound. So those ideas are there behind all this. So Q is in the set wise, right? And also in the Q, there will be an upper bound sitting after alpha. Just like 1 was there, for 1, the upper bound was pi. And that the proofs use that concept.
And so the real number line is like infinite.
Well, real number line, yeah, is infinite. Now, over here, of course, we're using our Q.
Not infinite line.
It is. It's not continuous, it's got holes. So it's not continuous because it's got holes, but it's infinite. There are those whole business of infinitely many going on, but it's not continuous, as in, I'm just reminding myself, no gaps, no holes. Somebody asks me in the class, no holes, no gaps. Okay, so we're going to do alpha is, so what is alpha? Alpha is we already know what that is, right? Alpha is and it's also, and also, this has happened to you last time in the class. All right. So alpha is the real number on the rational number line. Rational number line. And then I'm going to show it with this blue, this red here. Oh, actually not red. I need like, yeah, it's a problem. Okay. Yeah, I need to get another. Okay, this is better.
Maybe a purple.
And this maybe this is messed up. Okay. I'll do this. So everything in the red is a rational number. No, it doesn't. I can't put red here because this is the subset we're talking about. This, right?
But it is a subset of rational numbers.
Maybe I can put this color here. Okay, here we go. It's not on the number line. That's why it's kind of like this. I should even have a hole here, right? It goes where the hole was. And so it says, our picture is alpha is not empty, definitely not empty. And this goes on forever to the left. Okay. And goes to negative numbers. And alpha is the set. So this is what I need to do. The set here is not equal to this set here. All right, next to so number one is called that this is not trivial. This thing here, not empty, makes it non-trivial. Because an empty set, of course, is going to be a subset of Q. So, so let's write that. An empty set, of course, would be a an empty set, of course, would not be equal to Q. So an empty set, of course, would not be equal to Q, but this is a trivial case. If the set was an empty, it's automatically not equal to Q.
The trivial case.
Trivial case is this one, that of course the empty set is not going to be equal to Q.
It's trivial.
It's trivial. So this is the trivial case. What we want to make sure is that the non-trivial case is true, that not only is alpha not when alpha is not empty, it is still not. Yeah. So when alpha is not empty, so this is the kind of reasoning that's going on in the behind the scenes. When alpha is not empty, it is still not equal to Q. This is what number one makes sure. Number one makes this sure, this hold, and make this condition is the important one here. Now, if so, all right, so this was non-trivial. This one we've already seen. Now we're going to do downward to the left, including negative numbers.
What does the downward mean? That we mean
We're going to the left because the subsets, the real number is here, and the subset is going downwards to the negative. Kind of like the downward is coming from this one, right? Positive is up, negative is down. Yeah, so it should be, but the technical word is downward.
Leftward.
leftward. Or what was that show called? The Real World? No,
Westward?
Westworld. There we go.
Yeah.
It was pretty good until it wasn't.
Yeah.
Yeah, just dragged on too long.
I don't know.
Yeah. Yeah. Okay. If P belongs to alpha,
Down.
and again, what is alpha? Alpha is a real number. So we got alpha here. And I'm just going to put a red line here. Okay. So all the rational numbers to the left of alpha, alpha itself is an irrational or a real number. All the rational numbers to the left of alpha, right? And it says if P belongs to alpha, and I just want to point out something here, which we were kind of talking earlier. Infinitely many. Now, because there are infinitely many, if there's a P, so let's put the P in. P is a, we're using these as real numbers and alphabets as rational numbers. Okay. So we stick P in. It says if P is in alpha, it has to be here. Can't be here. So it fits right there. And then the next condition is and Q, another rational number, is less than P. We have Q to the left of P, right? To the left of P. Then, if this is the situation, then and then it says that Q belongs to Q belongs to alpha. Okay, so every time you pick a rational number in this subset and find a smaller number that is still in this set, you pick. So every time it will be true that you pick a P, there will be a Q to its left. Every time. So what's happening here is every time you pick a P, as much as possible to the left, every time you pick a P as much as possible to the left, you will always find a Q to two P's left, which basically means that the subset contains every number to the left. So yeah, alpha, the cut, alpha contains everything to its left. Every rational and also all the real numbers.
Oh, it also contains all the real numbers?
Because real numbers are sitting there too. We saw that, remember we had 1 and pi? Yeah, so there could be, we could have a representation of a real number sitting there and it's, so in other words, real numbers are made up of other real numbers too. But in the definition, we just stick with this. Okay, and that's why we have to think of, when we are comparing real numbers, we use less than. When we think of theirs as subsets, we use the this symbol here, the subset symbol. Or when we think of them as sets, we use this. When we think of them as numbers, real numbers, the cuts. When we think of cuts as sets, we use the subset symbol. When we think of the cuts as real numbers, we use the less than symbol. Okay, all right, number 3. And unfortunately,
I've run out of space.
We'll have to delete this little bit here. Now we have on number 3. And so number 2 was downward, as in this business and all of that. Number 3 says, if P belongs to alpha, no, sorry, belongs to. I just fixed it. If P is a element in the set alpha, which is the real number. Alpha is a real number that is that represents a subset, and P is in that. Alpha is represented by a subset in which P is a member. Then there is, and we now know what all this means. Then there is some R that also belongs to alpha. Such that R is greater than P. So we gotta do something here to represent this. Okay, so we have our Q line. This was Q. And then we have R alpha. And everything to the left of alpha, all the rational numbers and everything else. Okay. And then we have P right here.
R between P and alpha.
Yes. And why is it? Because?
Alpha is a first set.
No.
Or an alpha.
No. So right from here all the way to over here. Why is there a Q always to the left of P? Infinitely many. This is your friend, this phrase, infinitely many. From here all the way to minus infinity, there are infinitely many numbers. Okay. Now we go here. Between P and alpha are infinitely many R's. So if I move P all the way to here, like Jerry Lewis, you know, Jerry Lewis, the genius. So I'm right there, and the rational number line is just teeny weeny bit. There are infinitely many here. So as soon as I find, this is R, this is P, I'm going to find a R. I can never find what? To the right of any P, whatever R I choose will be, no, okay. In other words, you probably remember this. There is in a cut, there is no largest element. Because as soon as you find me, let's say this was our candidate max. As soon as you find me the maximum number, I'm going to say, look to your right. Yeah, the digits in a decimal, exactly. So so you have 3.1, then you have 3.14, then you have 3.141, and it keeps going. This is pi, right? So right there. So if pi is sitting here, what you have is, so here is our Q, pi is sitting here, and you go, oh, I found the max number in this subset, which represents pi. And I go, no, look to your right, there is an R, and that R is 3.14, and it's bigger than P. You go, okay, you know what? I look to the right of R before where pi is sitting, where the cut is sitting, and I go, hey, I found another, this number here. This is the max number. And I go, no, because between this max number, 3.14, and pi are infinitely many. And this is the example they actually use in the book. So as soon as I get, I don't know what the next number is, maybe 2, 5, oh, it is? Okay, yeah, that looks right. And then bam. Because these, of course, are non-repeating, so they go on infinitely many. Okay, so number 3 is insisting on, what number 3 guarantees for the representation of the real number is that if a real number is represented as a subset of rational numbers, there is no max in this set.
There can be no max.